In this lesson, we're going to build upon our understanding of probability distribution tables and look at the concept of expected value. Now you can see what it says there on the screen, but let me go through it. Expected value is the value you would expect from running an experiment many times. Often it is used with games of chance involving money, and the example I'm going to have a look at does that. And the EV tells you if the game is worth it. So in other words, if you gain more than you would lose over a long period of time. So pause the video and write those notes into your book, and then I'll have a look at the example. So hopefully you paused it. If you didn't, oh well. Here's the example here. A coin toss game costs $2 to play, and here are the rules and the outcomes. The coin will be tossed three times. If you get all heads or all tails, you'll win $20. Otherwise, you'll lose 5. What is the expected value? In other words, if you play this game quite a few times, what would the expected value end up? What would you expect to get at the end of those quite a few times? All right. In slide 3 there, we have a probability distribution table. Have a look at how I've set this up. These are the number of times I can get heads. I either get no heads, or 1 head, or 2 heads, or 3 heads. Okay, so remember, we always look at our random variable in terms of a particular outcome we're looking for, in this case. Heads. These are the probabilities that we would get. There's that 1, 3, 3, 1 that we looked at last lesson. For no heads, 1 head, 2 heads, 3 heads, and it's over 8 because 1 and 3 is 4 and 3 is 6 and 1 is 7. So it's 8. So there are 8 possibilities, and this is the distribution of those 8 probabilities. The gain is not quite what you might expect if you have a look at the example. It says $20 for a win, effectively, and $5 loss if you don't get that. So why are these numbers like so? It's because you need to factor in the fact that the game costs $2 to play. So if you win 20, then you're going to have to take off the outlay of money to start with, $2. That's why it's 18. If you lose 5, then you're going to have to take another $2 off. You're out of pocket $7, not just the $5. And similar for these two as well. And looking at slide 4 now, you can see how the expected value is actually worked out. So there's a 1/8 chance of getting 3 heads. The expected win from that 1/8 will be 1/8 of 16. But you could also get a loss of 7, so it's 3/8 times minus 7, plus another loss of 7 from 3/8 times. Sorry about that. That should say minus 7. Plus another 1/8 loss, 1/8 of a win of $18 from 3 heads. So if you add all that up together, you'll get minus 3/4, which could be written as minus 0.75. Now, what does that mean? That means that per game, you could lose 75 cents. Now, that doesn't really make sense, does it? You either win $20 or lose $5. How can you win 75 cents or lose, in this case, 75 cents? And the answer is this is an average value. Okay, so on average, you'd lose 75 cents, and you should know averages well enough by now to know that the average value doesn't actually have to be a specific value in your data set. Instead, it's, if all wins and losses were shared out evenly, each game would be a loss of 75 cents. That's what it means. I'll spell this out in the next slide so you can sort of see it for yourself. Expected value then is the mean. On average, you'd expect to lose 75 cents per game. On average, you'd lose $75 every 100 games. Okay, that's basically what it means. The expected value is a mean. And what you're doing is you're saying over a long period of games, if you then took your winnings and took your losses and then shared them out evenly across every game, what would that be? 75 cents per game loss. So you wouldn't play the game necessarily if you're looking for a game that was always going to return money. But of course, with a game, you're probably doing something a little bit more exciting, like hoping that you're going to win on the very first game and then you'll walk away, that kind of thing. But anyway, so that's basically expected value. I'm going to look at the textbook for a couple of more examples. It's probably the most efficient way of explaining what to do, and then you can have a go at doing some work yourself. So if I go to the textbook and we have a look at expected value, and you can see in the textbook it does say mean there as well. There's a couple of examples. Let's have a look at example 15. I'll zoom up a little bit. Like so. That's not zooming up very well, is it? Give me a tick. Okay, this one's using a money example as well. A person may buy a lucky ticket for $1. They have a 20% chance of winning $2, a 5% chance of winning $11, and otherwise they lose. Okay. Now, what they've done here in their table is they've just gone straight into a gains row up here, and then the probability of that win or loss is written down here. So where I had, oops, wrong one, sorry, where I had um, three rows. One was the sort of expected value. One was the outcomes. The other one was the probabilities, and now this is the actual gain and loss row. They've just sort of gone straight to the gain loss, and it made sense in its context. So again, I expect you to be able to do similarly. Do you need an extra row, or do you go straight for a single row for the gains and losses? So -1. Where does that come from? They have a 20% chance of winning $2, a 5% chance of winning $11, and otherwise they lose. There's 0.75. There's the missing probability that, well, it's not missing, but it's the one that's not explicitly stated in the problem. It's a -1 because they have to pay $1, and if they lose, they don't get anything more. Okay, so they've lost $1, 75% chance. 20% chance of winning $2. So that means that the overall gain would be $1, and you've got 20% chance. And then a 10% chance of winning $11. So that's $10 here. So that's 11 minus the dollar that you had to pay out, and a 5% chance there. And you can see the way they've calculated that for 1,000 games. Again, just reinforcing that sense that expected value is a mean, it's an average. So you can see here that they've just gone, well, that would be 750 games won at -1, not won, but played at a -1. 200 games would be played at $1 gain, and 50 games would be played at a gain of $10, which then, when divided by 1,000, gives you -0.05 or 5 cents per game. That's the expectation. 5 cents per game. So E of P in this case, because I've used P instead of X, is -0.05. Okay, example 16. There's a bit of sum notation here. You can read it for yourself if you want to get a sense of it. But it's basically just saying what we did before, adding up all the different values. So example 16, a coin is biased in favor of heads so that the probability of obtaining a head on any single toss is 0.6. So what does that mean about the probability of getting a tail on any single toss? The coin is tossed 3 times and the result is noted. If X is the number of heads obtained on the 3 tosses, find E of X, the expected value of X. So there can be no heads, 1 head, 2 heads, 3 heads. So what does no heads mean? No heads means that 3 tails were flipped. Each of the tails has a probability of 0.4. So 0.4 times 0.4 times 0.4 is, guess what? 0.064. 1 head would be 0.6 of getting 1 head. then 0.4 of getting the other one as a tail, and 0.4 of getting the other one as a tail. So you'd have 0.6 times 0.4 times 0.4 is 0.288. And similarly for these two values as well. Okay, the expected value then, E of x, which is the same as the mean, which we use the Greek lowercase symbol mu for that. So mu is the mean, mu is equal to E of x is the sum of x times P of x, and you can see that's what they've done there. I wouldn't bother doing that. I would go straight from E of x is equal to, and then I would just be going 0 times 0.064, 1 times 0.288, 2 times 0.432, and 3 times 0.216. Add them all up, and you get 1.8, which means that on average, every time you did that experiment, you would get 1.8 heads across the three tosses. Once more, it is not actually possible to toss a coin 3 times and get exactly 1.8 heads. That's not the point. The point is that you do that's the average over. If you played lots and lots and lots of games, that's what it would average out to be. That's expected value. Now, you'll need to do some work from your textbook. It'll be on Google Classroom, and it will be a few questions from exercise 13D. So in most cases, all you're doing is you're using the, let me see, let's try. I thought there was one with a table given. Say something like this. You're given a table, and you just need to work out what the expected value is. If it asks you for the mean, then that means the expected value, so it's exactly the same sort of working out. On the other hand, if it doesn't give you the table and you need to work out the table, then that's what you can do. I'll finish off by saying this. You can see how they worked out the expected value. Sorry, I've gone too far. In example 16, they've just added them all up. That's perfectly fine. Some of you might want to add an extra column and call it x times p of x kind of thing, and then do the multiplications bit by bit in your table, and then you can say the expected mean is, and then you can add up all the numbers that you worked out in your table. So that's another way of doing it if you want to. That does break down your thinking into little bits, which I do approve of. But if you don't need it and you want to go straight to this kind of calculation right here, then that's absolutely legitimate as well. It's up to you. Okay, I will leave it there. Have fun doing some expected value problems.